Hello students, today we are going to discuss about Gaussian Plume Dispersion model. Before going into the Gaussian Plume Dispersion model, let us see what is a plume. A plume is a smoke coming out of a stack or a chimney of an industry, or smoke coming out of the exhaust of vehicles, or the smoke released due to volcanoes or forest fire. Once a pollutant is emitted into the atmosphere from a tall stack or from any other source, it is transported and it gets completely dispersed into the atmosphere and may also undergo certain transformations. Now, to find out what is happening to the pollutant that is being emitted, we use the atmospheric dispersion model. So, the atmospheric dispersion model is a mathematical simulation of the physics and chemistry governing the transport, dispersion, and transformation of the pollutants in the atmosphere. It is also used, or it is a means to estimate the downwind air pollution concentration, given information about the pollutant emissions and nature of the atmosphere. So it is very helpful in finding out the concentration of a particular pollutant at a particular point in the atmosphere. From this figure, you can see that the atmospheric concentration at any point or at any receptor can be found out using a dispersion model, which is based on the data received from the topography of that area, the emission source information, that is the stack height, the source strength, etc. Then the meteorology, which may include the wind conditions, then any other receptors that are involved. So all these data are combined together and a mathematical dispersion model is used to find out the atmospheric concentration of the particular pollutant at any point or at any receptor. Gaussian plume dispersion model is a similar mathematical simulation method. The dispersion of the pollutant in the atmosphere is explained using the Gaussian plume dispersion model. It is the most widely used. It is based on some assumptions like the stack gas is transported downstream, that is in the windward direction. Dispersion in the vertical direction is governed by the atmospheric stability. That is how the pollutant is getting dispersed vertically upwards depends upon whether the atmosphere is unstable, stable, or neutral. Dispersion in the horizontal plane is governed by molecular and eddy diffusion. That is how the plume is spreading in the horizontal direction depends upon the amount of heating of the atmosphere, also depends upon the friction in the atmosphere due to some buildings or any other structures. The plume spread and shape vary in response to the meteorological conditions. For example, the wind direction or the wind speed help in finding out the spread and the shape of the plume. Before going into the details of the Gaussian dispersion model, we should be clear about the three axes used in the model. As you can see from the figure, you can see a stack which is emitting plume of the contaminated air. Now, through the stack passes the axis. The x-axis is represented by the wind direction, which is shown in red. the y direction or the y axis is transverse to the wind. That is, it is crosswind. The z direction or z axis passes vertically upwards through the stack. All these three axes are perpendicular to each other. And at the base of the stack, the value of x, y, and z is equal to 0. The height of the stack is assumed as h, and the effective height of the stack is capital H, which is the sum of the height of the stack plus delta H, which is the distance from the top of the stack to the plume line or the plume center line. The plume center line is an imaginary line passing through the center of the plume as it is emitted. This figure shows clearly how the dispersion of the pollutant happens. You can also see the plume center line, the three axes, that is the x, y, and the z axis, all of them perpendicular to each other. HS represents the height of the actual stack, and delta H is the plume rise, or it is the distance from the top of the stack till the plume center line, and effective stack height is the sum of the actual stack height and the plume rise. That is, HE is equal to HS plus delta H. Now let's see the Gaussian plume dispersion model. Assume that there is a point source such as a stack which is emitting a pollutant continuously into the atmosphere, and let the effective height of the stack be capital H. Based on this, rho A represents the concentration of a pollutant A at any point x, y, z in the three-dimensional field downwind of the elevated point source of effective height h, which is given as rho A x, y, z, h is equal to q by 2 pi u sigma y sigma z into exponential of minus y square by 2 sigma y square into exponential of minus z minus h the whole square by 2 sigma z square plus exponential of minus z plus h the whole square by 2 sigma z square. Here there are three terms. The first term, that is q by 2 pi u sigma y sigma z, represents the concentration of the pollutant A along the center line. The exponential of minus y square by 2 sigma y square represents the concentration of the pollutant in the horizontal direction, that is in the crosswind direction, y direction. Exponential of minus z minus h the whole square by 2 sigma z square plus exponential of minus z plus h the whole square by 2 sigma z square represents the vertical concentration of the pollutants, that is along the z direction. Here rho A is the concentration of the pollutant at any point in gram per meter cube. Q is the source strength in gram per second. Sigma y and sigma z are the spreading coefficients or standard deviation in the y and z directions respectively in meters. U is the average value of wind speed through the plume. The concentration are symmetrical about the y axis and the z axis. Now let's see the Gaussian Plume Dispersion model or the Gaussian equation for certain specific conditions. We'll assume that there is a stack with height h which is emitting the pollutant into the atmosphere. Now, for ground level concentration, the value of Z will be equal to 0. So, the concentration of the pollutant at the point x, y, 0, h is equal to q by pi sigma y sigma z u bar into the exponential of minus 1 by 2 y by sigma y the whole square into exponential of minus 1 by 2 h by sigma z the whole square. In the next condition, we are considering the ground level center line concentration. Since we are finding the ground level concentration, the value of z equal to 0, and for center line concentration, that is the center line is parallel to the plume line. So, the value of y equal to 0. In this case, the concentration of the pollutant A at x, 0, 0, h is equal to q by pi sigma y sigma z u bar into exponential of minus 1 by 2 h by sigma z the whole square. Next is the ground level center line concentration when source is also at the ground level. For example, the source will be at the ground level in case of a vehicle located on the road. So, here the source is at the ground level, so h is equal to 0. And since we are going to find out the ground level concentration, z equal to 0, and since we are finding the center line concentration, y is also equal to 0. So, rho A of x, 0, 0, 0 is equal to q by pi sigma y sigma z into u bar. Next is the maximum ground level center line concentration from elevated source. Since it is ground level, z equal to 0, center line concentration, so y equal to 0, and it is an elevated source, so the height of the stack h has to be considered. Here we are going to find out the maximum ground level concentration at the center line. And this is actually a modification of the third equation. So here rho A max at x, 0, 0, h is equal to 2q by pi u bar E h square into sigma z by sigma y. Next is for infinite line source ground level concentration. For example, if in an industrial area, if there are many industries located and each of the industries having its stack which is emitting the pollutant into the atmosphere, then we can consider it as an infinite line source. Here the source strength is considered as QL, which is the source strength per unit length. And here rho A at x, y, 0, h is equal to 2QL by 2 pi raised to 1 by 2 sigma z u bar into exponential of 1 by 2 h by sigma z the whole square. Next is for infinite line source located at ground. An example for an infinite line source located at ground is a traffic junction. In a traffic junction, there will be infinite number of vehicles and each of the vehicle will be emitting the pollutant into the atmosphere. So, since the source is located at the ground, h is equal to 0 and we are finding out the ground level concentration. So, z equal to 0. So, rho A of x, y, 0, 0 is equal to 2QL by 2 pi raised to 1 by 2 into sigma z into u bar. Now let's see the assumptions and limitations of Gaussian Plume model. The first assumption or limitation is that the model is most accurate for downwind distances between approximately 100 meters and 2000 meters. For distance below 100 meters, the value of rho A has to be corrected considering the wind flow pattern around the source structure. And for distance greater than 2000 meters, the local terrain features and meteorological variation has to be taken into consideration. The second limitation of the Gaussian Plume model is that the dispersion coefficients sigma z and sigma y used in the equation are not very accurate. Actually, the value of sigma z and sigma y are found out using certain tables and graphs. So, it may not be very accurate. Third assumption or limitation is that the model neglects the turning of wind due to frictional effects which can spread the plume to the crosswind direction. That is, due to certain frictional effects, that is the presence of buildings or some other structures, there will be turning of the wind and that can spread the plume to the crosswind direction. But this limitation is actually neglected. Next is the consideration of the adsorption or deposition of the pollutants when it reaches the ground is neglected. So, in actual situation, there will be adsorption or deposition of the pollutant on the ground surface, but that amount is neglected in the Gaussian plume model. The plume is considered to be non-reactive, but as we actually consider, suppose a pollutant like SO2 is being emitted to the atmosphere, it may react with the moisture in the atmosphere and form sulfuric acid. But in the Gaussian plume model, we are actually considering that the atmosphere is non-reactive and no such reactions are taking place, which is not actually true. So, this is also a assumption, or we can say it is a limitation. This figure shows an industrial building with a stack which is emitting pollutants into the atmosphere. In actual situation, if we see, there is time varying emission of the pollutant into the atmosphere. That is, the rate of emission of the pollutant is not constant. Also, if you see the plume behavior, the plume is not being emitted symmetrically about the plume center line. That is, there is fluctuation in the emission of the plume. Another thing is that in actual situation, certain reactions are taking place in the atmosphere. Here, as you can see, some amine chemistry and NOx chemistry is taking place. But in Gaussian plume model, we are actually neglecting it. There are certain dry deposition of the pollutant taking place. There is dispersion of the pollutant around the building or the industrial building, and there is changes in the surface roughness. That is, it is not a plain area. There is flow over complex terrain. We can see that there is precipitation happening. There may be order in the plume. There may be certain radioactive decay and gamma dose. But in Gaussian plume model, we are actually neglecting most of these situations. That is why there are certain limitations or assumptions for the Gaussian plume model. So, that's all about the Gaussian plume dispersion model. We'll see the application of this model in certain examples in the coming presentations. Thank you.